Hi everyone, welcome to lecture 25 of your circuit class, and the lecture is about phasor relationships. So the objectives of this lecture: first objective is to understand the phasor relationship for circuit elements. What we mean by circuits elements are the R, the L, and the C: resistance, inductance, and capacitance. And the second objective is to obtain the inductive and capacitive reactances. So these are the two main objectives of this lecture. So first we will start with the phasor relationship. For circuit elements. So if I have the circuit element here, over here we will have time domain, phasor domain, then we can go with the first one, that is a resistor. So for resistor we can express it in time domain like this: plus minus, that is V, this is the current flow in I, that is R. So our V in this case is equal to IR. Then in phasor domain we represent it like this: the voltage across it, that is phasor V, the current flowing through it, that is phasor I, and this is resistance. And then we can say phasor V is equal to phasor I times R. And then for inductor, in time domain the inductor look like this. So we will have our voltage V, our current I, that is the inductance, and the V across the inductor is equal to L di over dt. So if you look at our time domain expressions, all the time that we represent our quantities as in italic letters, and that is a standard in italic letters when it is in time domain. And then in phasor domain, this is phasor V, the current flow in here is phasor I, this is our inductance, then our phasor V is equal to J omega L times phasor I. That is for inductor. And then the last element here is our capacitor. For capacitor, in time domain, we express it like this. That is our capacitance C. The current flowing here is I. The voltage across the capacitor is V. Then in this case, we can express our I is equal to the capacitance C times dV over dt. And in phasor domain, this is our C. The current flowing here is phasor I. The voltage across the capacitor is phasor V. Then our phasor I is equal to J omega C times phasor V. And this is the, let's say, the time domain presentation and the phasor domain presentation for the circuit elements. So now, regarding the phasor relationships, for resistor, we say that voltage and current are in phase. That is the relationship, because all the time that the theta V is equal to theta I for the case of resistor. The second relationship here, that is for inductor. For inductor, all the time that current lags voltage by 90 degrees. All the time that when we have a pure inductor, the current flowing through that inductor is lagging the voltage across that inductor by 90 degrees. And the third one, that is for capacitor. All the time that current leads voltage by 90 degrees. So if we have a capacitor, the current flowing through that capacitor leads the voltage across that capacitor by exactly 90 degrees. So to determine lagging or leading, use my own expression, and that is C I V I L. So civil rule. So this over here is capacitance. This over here is current. This over here is voltage. This over here is current. And this over here is inductance. So if you look at that, at the civil rule, in the case of capacitor, our I came before the V. So I before V, that means I leads V. In this case here, I after V, that means I lags V in the case of inductance. So in the case of capacitance, I came before the V, that means I leads V. In the case of inductance, I came after the V, that means I lags V. Don't forget that. So the first term that here we should know called inductive reactance. Because look at this here, when we have our inductance, L is in Henry. However, we need to find its resistance. Its resistance called reactance, and that will be in ohm. So we can say the inductive reactance is a frequency dependent element measured in ohm and can be represented as X sub L is equal to Vm over Im. So if I have this inductance, the current flowing through it is I, and the voltage across it is V, and these are in phasors, then what we have to do to get the XL, which is the reactance of that inductance in ohm, we just take the magnitude of the voltage and divide it by the magnitude of the current. And that is equal to omega L, which is equal to 2 pi FL. So any of these formulas will be okay. If I have the voltage magnitude available and the current magnitude available, I can find the inductive reactance using these two quantities. If I know the frequency and I know the inductance, then I can use omega L. If I know the frequency in hertz, then I can use 2 pi f multiplied by the inductance L. That is XL. So look at this here. When we have DC, frequency is equal to 0. Then our XL is equal to pi times F, which is 0 times L, which is equal to 0 ohm. That's why we said that it will be short circuit. Remember that? That is for DC. So capacitive reactance again, that our C is in farad, so we need to find the resistance, which is called reactance, and that will be in ohm. So we can say that capacitive reactance is a frequency dependent element measured in ohm and it can be represented as X sub C is equal to Vm over Im. So if I have a capacitance, I know the current flowing through it is phasor I, and the voltage across it is phasor V. Then I can find the reactance of that capacitance by dividing the magnitude of the voltage by the magnitude of the current. Or this is equal to 1 over omega C. So if I know the capacitance value and I know the angular frequency, then I can use 1 over omega C to get that reactance. Or that is 1 over 2 pi Fc. And that is, of course, in ohm. So if you remember that for DC, X sub C is equal to 1 over 2 pi, and the frequency is 0 for DC times Z. That will be infinity. That's why we said that our capacitor will act as an open circuit in DC. Okay. So now what we mean by frequency dependent? Frequency dependent. Suppose that we have our L is equal to, let's say, 1 Henry, and our, let's say, frequency is equal to, let's say, 60 Hertz, right? Then from that, our X sub L is equal to 2 pi FL, right? And this is equal to pi times 60 times 1, right? So that is equal to 2 pi 60. Now, if our L is equal to 1 Henry, which is the same element, same inductance, 1 Henry, however, our F is equal to 120 Hertz, then our X sub L is equal to pi FL, and that is equal to 2 pi times 120 times 1, which is 2 pi times 120. So if you look at that this value here is double of this value, right? So that's why we are saying that it depends on the frequency. So the frequency will affect the value of the reactance in the case of inductance and in the case of capacitance. So let us go over an example over here. So we do have a black box so the set of voltage and current is given by V of t is equal to 1000 cosine 377t plus 10 degrees, and our I of t is equal to 5 cosine of 377t minus 80 degrees. So what we mean by the black box, so I have a black box like this, and I have two terminals for this black box. So when I measure the voltage here, it gives me this sinusoidal waveform. And when I measure the current flowing over here, it gives me this value. So we need to know what this black box contains, like what is the element inside of that black box to have when we apply a voltage of 1000 with angle 10 degrees, we get a current of 5 with angle negative 80. So let us do, so in this problem here, we need to determine the circuit element involved, whether it is R, L, or C, and determine its value in its proper unit. What we mean by that, if it is a resistance, then that should be an ohm. If it is inductance, that should be in Henry. And if it's capacitance, that should be in Farad. That is the proper unit for that, let's say, element. So solution. So we can say that from the voltage and current phase angles, we can determine the phase relationship. So if you look at this here, two time domain expressions, that is in cosine, this is in cosine. Since we are dealing with the same element, then for sure that the angular frequency are equal. So if you look at that here, the voltage leads the current, right? So we can say voltage leads current by, and if you look at that, 10 minus 80, 10 minus negative 80, and that is equal to 90 degrees. So in this case, when we are saying that voltage leads current by 90 degrees, that means at the same time current lags voltage by 90 degrees. So we can use here CI VIL, civil rule. So since the current is lagging, so the current here came after the V, then the current is lagging, and that is by 90 degrees, then that is inductance. So the element is L. So now, how we can find our, let's say, value of that inductance? First, we need to find the reactance. XL is equal to Vm over Im. Vm is given in our voltage expression, which is 1000, and Im is given as 5. So this is equal to 200 ohm. So this is the inductive reactance. So now, as you know, our X sub L is equal to omega L, right? So XL is 200. That is equal to omega. We go back here and see the value of omega. So that is 377. So we put over here 377 times L. Then L is equal to 200 divided by 377. and that is equal to 0.531 Henry, and this is the value of the element involved in that black box. By this, our lecture 25 is complete, and it is done, and this is your homework for this lecture. So we have 2 problems with the black boxes, and you need to find the elements involved. Thank you for watching.